And the next contributed session is going to be chaired by Stephen Wu. So I'll give the floor to him.
All right, thank you. And thank you, Patricia, for this wonderful talk. So we have an exciting section coming up with 4 talks, contributed talks. The first talk is given by Peter Biswas from Indian Institute of Science. Peter, can you try do screen share on your side?
Yeah, sure. Am I audible?
Yes, we can hear you. We cannot see your slides yet.
Yeah, I'm sharing my screen.
Now we can see your slides. Thanks.
Great. So let me just do the slideshow. Yeah, so is it full screen now?
Yep, go ahead.
Okay, great. So hi everyone, I am Arpita. Today I'm going to talk about our work on infra-marginality audit of group fairness. This is a joint work with Siddharth Burman, Amit Deshpande, and Amit Sharma. Wait. Okay, yeah. So in this work, we propose a definition for the degree of infra-marginality, and I'll talk about it in details. It's basically a measure of fairness. And we also prove theoretically that infra-marginality and accuracy are dependent on each other. And we also propose a methodology to audit infra-marginality of classifiers. We show that it's possible to maximize accuracy or find optimal classifiers under infra-marginality constraints. So our focus is on binary classification. So here we assume that there's a classifier which labels each data point as either positive or negative. We additionally assume that each data point X has a probability P star associated with it, and this is the inherent probability of this data point to be in the positive class. So that's given by P star X. And there's a label which is Y star X, which is Bernoulli drawn with probability P star X. Now, traditionally, the goal of classification is to find a CX function such that it is as close to this YX star as possible. And hence, we generally try to maximize accuracy. But what about fairness? So here we again look at the fairness notion, which is called individual fairness, where the idea is to treat similar individuals similarly. In particular, we look at a single threshold fairness notion, where it says that the decisions that should be taken should use a single threshold on the true outcome probability P star X. So let me show these graphs to make you understand what are we trying to capture. So let's say here we plot the distribution of probability of 2 different subgroups in a population, z equal to 1 and 0. And in order to maximize accuracy, we figure out that this tau equal to 0.5 is the best threshold. And everybody on the right side of this threshold can be classified as 1. Everyone in the left side can be classified as 0. And this is good. This is also, this adheres to the single threshold fairness notion. So let's call this labels F stars. That is, whenever it's on this side, it's 1. Whenever it's on the right side, left side, it's 0. Now, let's say we try to use another classifier where group fairness is imposed. In particular, this graph is trying to maximize accuracy subject to the fact that the fraction of positive labeled individuals should be same in both populations. So to do so, a threshold-based classifier would have to have 2 different thresholds for 2 different groups in order to ensure that these 2 shaded areas are equal. However, while doing that, there's a fraction of population who would get a very different label than what the fair labels would have done. So to capture that, we propose this matrix called degree of infra-marginality, and we quantify this. So this basically says that it captures the extent to which a classifier's output is different from this F star X labels for individuals whose inherent probability P star is more than epsilon distance away from some given threshold. So it's a very conceptual idea, and the reason we propose this is to again show that how different single threshold fairness can be from to another classifier that simply imposes group fairness. So note that here we assume any binary classifier and need not be a threshold-based classifier. The classifier can have any, I mean, it just has to be a binary classifier for this measure. What we see is that on a synthetic data set, we show that if you just maximize accuracy, the infra-marginality measure would be very low. However, if you put a lot of penalty on group unfairness, then gradually the infra-marginality increases. And in fact, if you have a lot of penalty on group unfairness, then the resulting classifier can have almost 50% infra-marginality. That is, almost 50% of the population is given a very different result from what it was getting under maximizing fairness. Of course, this shows that there's some inherent dependency between infra-marginality and accuracy. So we show that theoretically. Also, we propose that if you do not have a P star, you can somehow estimate P hat, the P star as P hat, and then propose a surrogate infra-marginality term to do the audit method. So the basic takeaway is that we propose the inclusion of infra-marginality as an individual fairness matrix in the work on auditing fairness for algorithmic bias. And the immediate open question is, can we show this theoretical dependence between various group fair notions and infra-marginality together? So yeah, I would like to gratefully acknowledge this grant, and thank you so much for your attention.
All right, thank you, Apita. So we have time for a few questions. So you could leave it in the Q&A section, leave it in the chat window, or if you feel like speaking up, you can also raise your hand. I can unmute you. So while we're waiting, I do have one question.
Sure.
Does your framework of infra-marginality also naturally translate to not just binary classification, but some sort of multi-labels? You know, sometimes many systems have like the labels such as very likely, somewhat likely, just like, you know, paper acceptance system somewhat. Yeah.
Actually, if I go back to the definition, it uses this F star X, and this F star X is generally, so we are assuming that this F star X is obtained by this kind of a thresholding on their true inherent probability of being in the positive class. So this generally makes this F star X either 0 or 1 every time. Hence we only focus on classifiers which are binary. However, for multi-class, I think it is possible to bucket this F star X as into more labels. If the categories are more like an ordinal categories, we can do that. And then maybe the CX can also be extended to the multi-class classification, but it needs to have some ordinal dependencies.
Great. So we have one more question. While we ask that, can Chris, can you set up and maybe you can allow Chris to share a screen. Yep. So the question is, can you restate the intuition behind why infra-marginality correspond to fairness? Peter, you might have to disable your share screen to allow Chris to.
Oh, okay. Yep. Yep. Yeah. Okay, so
the question is yeah, go ahead.
Yeah, so here we are trying to capture individual fairness or the single threshold fairness as a benchmark. And somehow infra-marginality captures the fact that if you would have a single threshold best classifier according to that F star labels, then that should have been like the classification that you should have done, but then you're imposing group fairness or other constraints and you have something else. So how much are you deviating from the F star label? So that's the idea of, and it's very conceptual. We were trying to find out different relationships in a more theoretical way. I would say it's a very conceptual work.
All right, great. Thanks, Peter. So let's move on to the next talk. We'll have Christian from Penn. All right, take it away.
And you guys can see the slides and hear me?
Yes.
Okay.
Right.
Hi, everyone. My name is Chris, and thanks for tuning in. And today I'll be talking about service in your neighborhood, fairness and center location, which is a joint work with Sampath Khanna and Neil Lutz. So in recent years, there has been a lot of algorithmic fairness research, but we realized that a lot of those research has been focusing on the supervised settings, and there hasn't been as much work in the unsupervised settings where you're only given a collection of features and not a label. So we started to think about what are some things that we can, what are some kind of problems, and we thought clustering problems will be an interesting problem where clusterings are used to solve infrastructural decision problems, such as where should we place hospitals, schools, library branches, police or fire stations. And we thought that these question of where to place these locations of these facilities are important, because once the decisions have been made, it's a lot harder to revisit the decisions for these kinds of infrastructural decisions. But we do acknowledge that we weren't the first people to think about fairness in the clustering domain, but we take a little different approach than the previous work, and I'll get into that now. So we wanted to come up with a fairness concept that tries to take population density into account, and by doing so, we had two goals. We wanted to make sure, first, outliers will not disproportionately affect clustering outcomes, and also we wanted to have that these clustering sizes are roughly equal. And I'll kind of get back to as to why these are desirable goals in certain contexts. And to that, before going into that, let me just define this thing that we call neighborhood radius of an individual eye. We formally define it as the minimum radius of a ball centered at individual eye to contain n over k individuals, where n is the total number of points and k is the number of centers you want to place. So here I have an example, simple example. We have 10 points and we want to place 2 centers. And for the person on the left, it's the neighborhood radius is basically the radius defined by the ball that you need to. It's defined by the ball that I have drawn on the left, and that ball encapsulates 5 individuals, which is 10 over 2. But as for the person on the right, the neighborhood radius is a lot bigger because it's this person is in a more sparse region. So this neighborhood radius kind of gets at the population density. And we want to find a solution such that each individual will be able to find a center within his or her neighborhood radius. But unfortunately, this is theoretically impossible. So we wanted to kind of optimize how far we deviate from this ideal. To that end, we say that algorithm satisfies alpha fairness if it's a case that for every individual, the ratio between the distance to the closest center for individual eye and the neighborhood radius of the individual eye is n most alpha. And so our goal will be to minimize this alpha. And here I come back as to why this makes sense in certain contexts. So first, taking population density into account is is important because people living in with different population densities will have different expectations for a reasonable distance to travel to a center. So if you're living in a rural area, maybe it will be totally unreasonable for you to expect it to find a hospital within a mile. Whereas if you're living in an urban area, that might be a reasonable expectation. And second, it does achieve intuitively some kind of load balancing of the centers, because low alpha will try to place more centers in denser regions. And with that, you're not going to overwhelm centers in urban regions, and it's not going to be the case that the centers in rural areas will be so empty by contrast. And in this setting, here are the results that we have. We show that in any metric space, the best alpha you can achieve, it will always be greater than 1/2. And we also show that there exists a metric space such that no algorithm can achieve alpha fair for alpha strictly less than 2. And in Euclidean space, that 2 becomes the square root of 2. And we also show an algorithm that can actually achieve alpha equals 2 in any metric space by borrowing some similar idea in the metric embedding literature. And as a corollary, because we know that any metric space, in any metric space, alpha has to be greater than 1/2. This is a FORC approximation algorithm. And we show that theoretically that minimizing this alpha is NP hard. And we actually run some empirical simulations on 2 geographical data sets. And here's what it looks like for the first geographical data set, Fairfax County. This is what it looks like for K-centers, K-means, and K-medians. And on the right, this is what it looks like for our algorithm. And we do the same for another geographical data set. And that's it. You can find the full paper and this archive link. And thanks for tuning in.
All right. Thanks, Chris. We also have time for maybe 1 or 2 questions. You can do the Q&A, chat, or raise your hand. I have one maybe rather general question about your framework. It seems like the objective is rather worst case. You look at the worst case individual, how far it is from the facility. Is there a way to, does your algorithm handle somewhat interpolation between worst case and average case? Maybe not the exact worst case individual, but maybe some measure of how bad like a fraction of the population might be.
Right, yeah, we actually haven't thought about that, or we did think about that, but we haven't really made any progress on that. So yeah, our algorithm is kind of like a case-centered thing where we were looking at the overall, like the worst case, but it would be interesting to look at maybe just even the sum of alpha over every individual or some kind of distribution. But yeah, we haven't actually made any progress on that route.
Right. Potentially, you can also try to see whether your experiments already exhibit some of these properties.
Right. Yeah. So I think from what I remember from the experiment, yeah, I think it was a few cases where they had really high alpha, possibly by those outlier points. But I think most of the points tend to have smaller. So maybe theoretically, if you assume maybe some kind of distribution over points, maybe you can get better expectation overall. But yeah, that would be an interesting future direction.
Great, thanks. While we're wrapping up, Christina, could you start your screen share of your slides? All right, so let's move on to the next talk. We have Christina Eventel again from Harvard, telling us about individual fairness in pipelines. Take it away. Christina, we cannot hear you for some reason.
Can you hear me now?
Now is perfect, yeah. Okay,
great. No longer just chattering into the void. Stephen, sorry for the technical difficulties. So today I'll be talking about joint work with Cynthia Dwork and Mina Jagadisan on individual fairness in pipelines. And I am incredibly lucky to have them as collaborators. Some of you may know that Cynthia was awarded the Knuth Prize this year, and Mina just graduated from Harvard, and I would quickly run through all 5 of our minutes, just trying to list her most recent awards and accomplishments. So I'll restrain myself and get on to the talk. All right. So I think at this point, it's pretty well understood that taking components that are fair in isolation and putting them together won't necessarily result in a fair system. As Ricky mentioned yesterday, an advertising platform may have no intention of bias, but legitimate competition between advertisers can still result in skewed delivery of ads. Feedback loops and repeated classification can also amplify unfairness, although the amplification is bounded. And even selecting a set of individuals of a given size can present subtle fairness challenges. So in this work, we consider the problem of cohort pipelines, which consist of a sequence of cohort selection and scoring steps in which each step can depend on prior outcomes. So for example, a company might hire a team of engineers and then promote the top performer a year later, or a university might admit a class and then allocate financial aid to those most in need. The problem here is that whether a particular person is the top performer or the most in need critically depends on who they were selected with. Okay, so let's have a look at a more specific example. So we have a set of job candidates, and we'll denote the highly qualified candidates with a very fancy hat. And suppose that the company hires either team 1 or team 2 with equal probability. And notice that all of the candidates, regardless of their talent level, are hired with equal probability. So we don't have any fairness concerns yet. Now, a year later, the company promotes the top performer on the team that they chose. So if we zoom in on team 1 or team 2 alone, there's nothing really wrong with this procedure. Within each team, the most qualified candidates are promoted with equal probability. But the problem becomes clear when we look at the pipeline as a whole. Because qualified individuals are hired into different cohort contexts, their chances of promotion can be arbitrarily different, even though they're equally qualified. And in fact, there are many ways a malicious company could exploit the interaction between steps in the pipeline. For example, by ensuring that all highly qualified candidates that they don't like, for whatever reason, are always paired with a slightly more talented candidate that the company prefers. But this issue can also rise unintentionally, even when the pipeline designer is explicitly trying to promote fairness. For example, the person designing the hiring procedure might try to put a pair of highly qualified individuals from an underrepresented group together so that they might provide mutual support or mentorship, or just to make sure that they end up on a team with high average qualification, not realizing that this might actually hurt their chances of promotion later on. Okay, so how do we fix it? Well, one approach could be to require that the hiring procedure and promotion procedure have to be designed together at the same time, and we force them to play nice by design. But this locks the company into a single strategy, potentially years in advance, and it ignores the fact that these decisions may be made at different points in time by very different sets of decision makers who may or may not even know about prior steps in the pipeline. So a manager deciding whom to promote may be completely unaware of an automated resume screening procedure that was applied to their team members potentially years prior. Okay, so rather than requiring a single monolithic design or requiring later steps in the pipeline to be fully aware of previous steps, we instead define the more realistic problem of robust cohort selection. That is designing a cohort selection mechanism which composes well with any scoring function from a pre-specified family of scoring functions. For example, scoring functions which don't change too much if a single individual is replaced in the cohort. This allows the company to choose a scoring function to adapt to changing market conditions, but also clearly specifies how the cohort selection mechanism and scoring function should work together. In the interest of time, I will give some very brief highlights from the rest of the paper. The first is that we give a large set of examples illustrating some of the subtle fairness properties relating to cohort pipelines. In particular, we discuss ways to capture differences in the certainty of outcomes, and we give a new measure on differences in distributions over outcomes that better captures small differences in scores. We also give constructions for robust cohort selection for two broad families of scoring functions, and loosely speaking, robust cohort selection boils down to ensuring that similar individuals have similar distributions over cohort contexts. That is that you have similar distributions over cohort contexts in which all of the functions in the scoring family will treat the pair similarly. Okay, with that, I will wrap up. Mina is also on the panel, and we're happy to answer any questions you have now. Mina, is there anything that you wanted to add or any questions in the Q&A that you wanted to address?
Mina, you're muted actually.
Oh, whoops, hi. I can maybe talk about the question with tournament design.
Yeah, go ahead.
Read the question out.
Yeah, so the question was, how does this problem relate to tournament design? So basically we're focusing on kind of one step in this, like in this talk of like selecting cohorts and then having the scoring function afterwards. But our framework can also be extended to many steps. So tournament design, we can think of as like grouping teams into like smaller collections and then having like a funneling system to eventually select the top. And so this also runs into similar issues of different, like based on the way you perform the initial grouping might lead to like, for example, super strong teams being facing each other in the first round. So the framework of having similar, like similarity in terms of like cohort selection in the first step can also be applied to the tournament setting of making sure the first grouping over teams is gonna compose well with future groupings over teams. So it also kind of extends to that setting, also to like imagining hiring pipelines where you have resume screening and then interviews after. So different multi-step funneling pipelines as well.
Great. Another question from Guy Wathlum. Do similar issues come up with other fairness notions, for example, group fairness, or positive results also possible for such alternative definitions?
Right. So yes. So I think the intuition here certainly applies to other definitions of fairness. And when you think about, so I think a good test here would be to think about conditional parity. Sorry, I lost that for a moment. So anything that we put together that's individually fair, so we provide robust constructions for satisfying individual fairness. So those should be translatable to satisfying conditional parity, which will allow us to cover most of the popular group-based definitions. I think that in general, we view solving individual fairness as kind of like the harder instance of the problem, and it should be relatively straightforward to extend these constructions to group definitions.
Great. Another question in Q&A from Haro Kanemaker. Can this apply to gerrymandering?
So I'll say yes and no. Yes, in the sense that the principle of who you're with really matters, and that tools here may be helpful for understanding more about gerrymandering. I think the objective of what counts as fair in voting is perhaps a little bit less straightforward than what counts as, than what we might say we can describe really nicely with, for example, a metric for individual fairness. It's not necessarily, I don't think there's a one-to-one correspondence here. Nina, do you want to add anything to that?
Yeah, maybe I can also say that, so we were also considering settings where, like if you place more and more restrictions on what types of cohorts, so what types of groups are acceptable, the cohort selection mechanism has more and more constraints. So what we try to show in this work is like two families that have some level of constraints on the cohort, types of cohorts that are acceptable that allow robust pipelines, but gerrymandering would be interesting in that the types of cohorts that make sense also has more constraints, but potentially ideas from this framework could be used in that setting, but it would require some more work.
Great. I guess I have one maybe basic question. So the definitions seem to be restricted to a two-stage composition, where you have F composed with A. But does it encapsulate potentially multi-stage composition with like more than 3 or 4? Yeah.
Right. So we're presenting the two-stage version. So what's interesting about the two-stage version is it can go wrong even with just 2 stages. You don't need a lot of complexity for this to bite you. But yes, this can be extended beyond just 2 stages. And Nina, do you want to say anything more about that? I am completely forgetting whether that's actually in the appendix or not.
It's not in the appendix, but I think it like the similar intuition can be used, but kind of like the tournament design setting, as you add more cohort stages, you have to be kind of careful at how these interplay with each other. As you add more scoring stages, you similarly have to be careful, but I think like the baseline framework turns out to generalize pretty well to the multi-stage setting.
Good, that's great to hear. All right, so let's move on to the next talk. How can you start your screen share of your slides?
Yes.
All right, so the last talk of this session, we have Hao Wang, also from Harvard. He will tell us whether to split or not to split. Take it away.
Cool, thanks. Thanks, Steven, for the nice introduction. And my name is Hao. I'm a fourth-year PhD candidate at Harvard. And I'm very excited to be here talking about our recent project on to split or not to split, the impact of disparate treatment in classification. And this is a joint work with Xiang, Mario, and my advisor, Flavio. I'm going to start with an illustrative example. So assume a data scientist wants to train a classifier for predicting pneumonia. They have samples with features such as chest X-ray. Among all these features, there's a legally protected sensitive attribute such as race or gender. So a natural question is, should the data scientist use the sensitive attribute in the classifier? And roughly speaking, there are three strategies for training this classifier. And first, the data scientist could disregard the sensitive attribute and use all other features to train a group-blind classifier. When the group-blind classifier is deployed on new fresh sample, it doesn't require the sensitive attribute as an input. The second strategy is to incorporate the sensitive attribute as an input and train a classifier using all the features. This is called a coupled classifier. When a coupled classifier is applied to new fresh sample, it requires not only the features, but also the sensitive attribute as inputs. The last strategy is to split the dataset based on the sensitive attribute and train a separate classifier on each subgroup. We call them split classifiers. In the testing time, split classifiers are deployed on each separate group respectively. So to summarize, a group-blind classifier doesn't use a sensitive attribute as an input. A coupled classifier uses a sensitive attribute while sharing other parameters. Split classifiers are a set of classifiers trained and deployed on each separate group. In Dwork et al. 2018, the authors considered how to use a sensitive attribute when it is ethical and legal to do so. They compared the performance of coupled classifier with split classifiers, and they showed that using a coupled classifier may lead to an inherent accuracy trade-off between different groups. In this work, we take a step back and consider another two fundamental questions. Is it always beneficial to use a sensitive attribute in the prediction task? When does using a sensitive attribute benefit model performance the most? We achieve these goals by comparing the performance between group-blind classifier and split classifiers. This is a non-trivial task. On the one hand, the performance of the classifier relies on the data distribution, and this probability distribution may vary across different groups. Therefore, using a group-blind classifier may incur an inherent accuracy trade-off between different groups. On the other hand, when sample size is limited, training split classifiers may suffer from overfitting and achieve higher generalization error. Hence, there are many factors that will determine the effect of splitting classifiers. For example, the difference of data distributions between groups plays an important role. It is natural to expect that splitting classifiers doesn't bring much benefit if different groups have the same probability distribution. And we make this intuition precise and provide conditions under which splitting classifiers doesn't bring much benefit or brings the most benefit in terms of model performance. So in this paper, we study the fundamental impact of incorporating a sensitive attribute in a classifier. We achieve this goal by comparing group-blind classifier with split classifiers. We study this problem from an information theoretic perspective, in the sense that we assume the underlying distribution is known and consider how this probability distribution impacts the effect of splitting classifiers. And this is a quick overview of this paper. So in this paper, we study the effect of incorporating a sensitive attribute in a classifier by comparing the performance of group-blind classifier with split classifiers. We introduce an information theoretic quantity called the benefit of splitting. which measures the performance improvement by splitting classifiers. In order to understand when splitting classifiers brings the most benefit in terms of model performance, we provide upper and lower bound for this quantity. And we also present an efficient procedure for computing this quantity. We also extend our analysis to the finite sample regime, in which splitting classifiers is not necessarily beneficial in terms of model performance. And thanks for listening. The full version of this paper can be found at arXiv.
All right, thanks, Hal. We can now take a few questions. And again, you can do it on the Q&A chat or raise your hand if you like speaking up yourself. So I do have a question. It's a very interesting result. One general question I have is, how does this impact depend on the hypothesis class you choose? For example, if you decide to use decision tree, that doesn't sound like a restriction, right? Like a split classifier really is introduce the first layer in the tree as taking the protected attribute to split up. And then further down, you just deploy really the same thing. And if your hypothesis class can approximate decision tree or tree-like functions, well, maybe this is not such a trade-off. Do you know whether your results say anything to that?
Yeah, that's a good point. So yeah, you're absolutely right. So the benefit of splitting depends on the hypothesis class, and so in our paper we have an example showing that under the same setup, the same probability distribution with different hypothesis class, the benefit of splitting can be completely different. And I'm gonna go back to the overview. So we provide bounds to understand when splitting classifiers benefit model performance. And those bounds shows that there are two factors that could affect the benefit of splitting. And one factor is your disagreement between the optimal classifiers. So basically for two groups, you train the best classifier on each group within your hypothesis class. And you compare their disagreement. If this disagreement is small, so intuitively speaking, there's no benefit because like the optimal classifiers are the same across groups. But if this optimal classifiers are different, and somehow like by our lower bound, there are scenarios in which you can achieve more benefit by splitting classifiers. Yeah, but that's a good question.
Great, thanks. I guess one thing that may be related to the talk earlier today, does your work connect to Patricia Williams' earlier story about osteoporosis, if you were in the earlier session today?
Yeah, so can you elaborate a bit more on this topic?
Yeah, actually, Cynthia, would you mind elaborating this a bit more?
We have time?
We do.
2 minutes.
So Patricia Williams talked about an algorithm that had a very, very different treatment for African-American women than for non-African-American women in the context of eliciting questions surrounding osteoporosis. So here you're talking about a classifier that may sort of be completely different for different races. Can you comment about the connection between what you're talking about and what she was talking about? And you specifically brought up a medical context. So can you comment on this?
I see. So basically, I guess, so I'm going to go back to the definition of fairness we follow. So like in literature, there's a standard, many standard commonly used group fairness measure, they measure the performance disparity between groups. But here, the measure we follow is do not harm. Basically, each subgroup should achieve the best performance on their So each subgroup should achieve their best performance. And we achieve this principle by splitting classifiers. And that's how, like, like different subgroups, they may have I mean, in terms of probability distributions, they may have different distributions. So by splitting classifiers, you may achieve better performance or the most suited classifier for each group. And that's how we achieve this goal.
So, it's really important to note that in a medical context, race is not a coherent notion. So I suggest that in the future you use a different motivating example and be extremely careful for the medical examples.
Yeah, I mean, in this case, like I used gender, I didn't use race. Yeah, but you're right. Yeah.
All right, so that wraps up the session in the morning. We'd like to thank all of the speakers this morning for giving their wonderful talks. And I guess the morning section is over. Aaron, do you want to chime in and say a bit about lunch?
Yeah, so we now have a lunch break. For those of you who attended yesterday, you know how to do it. For the rest of you, if you registered for the conference, you will have received an email from me on Friday that has a link to a different Zoom meeting. If you want to join for lunch, log off of this meeting and log on to that meeting right away. I will divide you into breakout sessions so that you can have sort of more intimate chats with a smaller group of people over lunch. Feel free to take 10 minutes to get lunch, but please sign into the Zoom meeting, the lunch Zoom meeting right away so that you'll be placed into a breakout session. And I'll see everyone back here at 1:30 for John Kleinberg's keynote talk.
All right, thanks. Thank you, everyone. See you at lunch.